Okay, so we are going to talk about QR algorithm or QR algorithm. So for finding eigenvalues. And again, so the idea is that just to explain why it works. So explain the algorithm, explain why it works. But unfortunately, it's not easy to give a detailed proof. Okay, so remember that the algorithm worked by starting with doing a QR decomposition, factorization of the matrix A. So here we have a so in principle it can be used also for non-symmetric matrices, but we will restrict to symmetric. So it's also sometimes works for non-symmetric matrices, assuming that they have a real eigenvalues. But we assume that A is symmetric n by n matrix, and so well, and Q and R. So again, so Q and R, it's in general kind of applied to any matrix, not necessarily symmetric, not necessarily square. So, but Q is if the matrix A is square, then Q is orthogonal, right? Orthogonal matrix. And so Q star Q is equal to identity, and Q star is equal to identity, and R is upper diagonal. No. And it is assumed that diagonal elements are greater than 0. And so this is just a kind of the assumption, and the algorithm works by writing that so K1 is equal to RQ, and so just and after that you kind of continue to do it. So you write that A1 is equal to so we only think that how we kind of choose the indices. So A1 is so I choose here A1 is equal to well, more or less natural Q1 R1, and so it's QR decomposition for A1. So in this case we define, so this is kind of A2 equal to R1 Q1 and so on, right? So the general would be A, say K minus 1 is equal to Q K minus 1 R K minus 1. Yes, so a K is equal to R K minus 1 Q K minus 1. So I'm not sure kind of if it's, so in this case this would be 0, right? So in this case this is Q0 R0, and okay, so this would, so here A is just the matrix with index 0. Okay, so this would be kind of R0 Q0. Okay, so now so the claim that AK converges when k goes to infinity to lambda where lambda is the matrix of eigenvalues, so diagonal matrix of eigenvalues. Right. So lambda is lambda 1, so lambda n 0, 0. Okay, so this is the claim. And so in practice, actually, it's not applied to just kind of like that. In practice, it's usually before that, before applying this algorithm, the matrix A is pre-processed and changed by orthogonal transformations. So by orthogonal multiplication by orthogonal matrix on the left and it's adjoint on the right, it's first of all preprocessed to be tri-diagonal, but it's not really kind of so important for us. So just kind of it's much faster to do first of all a preprocessing and reduce this matrix to tri-diagonal form. It's easy to. It turns out that it is easy to do. Right? And after that, kind of apply this QR method. Okay, so this is like it's done in practice. But we just kind of look at this specific example and kind of want to figure out why kind of this is true. And so the first step is so first one, so claim one is claim one. So AK has the same eigenvalues as A. And so when we do this transformation, we always kind of get a matrix with the same eigenvalues. So and kind of the idea is that it's the same matrix, same eigenvalues, but off diagonal elements become smaller and smaller and smaller, and finally we'll get a diagonal matrix with the same eigenvalues, and this is a lambda large. And so why this is true? So if you look at, say, so let us look at A1, for example. So what happens with A1? So A1, by our definition, is equal to this RQ, right? And what is R? Right? So I1 is equal to RQ. And if you look at what is R, so from this equation, right? So this is a orthogonal matrix. Right? So we can multiply this equation by Q star on both sides, and we'll get that R is equal to Q star multiplied by A. Right? So this is equal to Q star multiplied by A multiplied by Q. So we can adjust R in terms of, right? But this is if it's if this is a orthogonal matrix, then it means that it's a similarity transformation. Right? So it's Q minus 1 Q. Right? So, and at some point, kind of in there, we proved that similarity transformation do not change the eigenvalues. So you multiply on the one side by X, the matrix X, on the other side by the inverse of this matrix, eigenvalues do not change. And Q and Q star, they're inverse of each other. So it's a similarity transformation. Similarity transformation do not change the eigenvalues. So A1 has the same eigenvalues as this one. And well, kind of, we could also write here maybe Q 0, right? So Q0 maybe. And so if we kind of use this notation like here, and so A1 is equal to Q1 R1. So we started with A, so kind of we could write here Q0. And so now after that, what would you do? Kind of, you would have a A2 is equal. Right? So this is with the same procedure. You would get the Q. You would get Q1 star multiplied by A1 Q1. Right, and this is the same thing, kind of, right? So the eigenvalues do not change. So it's clear that eigenvalues will never change. And so this is proof with claim 1. So AK has the same eigenvalues as A, and so can you just repeat? So eventually AK will be equal to Q K minus 1 star AK Q K minus 1. Right? And right, so also we can write, so from this it also follows that we can write this formula. So we can write it, actually we can express AK. So it's it just, so here, for example, it would be Q1 star Q0. So and after that we plug in the expression of A1 in terms of the original. So Q1 star Q0 star A Q0 Q1. So like that. So we can, okay, so in general we will have something like that when AK is equal to Q K minus 1 star Q K minus 2 star so on Q0 star A, and after that this is Q0, okay, so on Q K minus 1 Q K minus 2. And so we'll denote this somehow. So let me see the notation that I used. So see here something like something I did wrong. So so the notation is wrong here in the lecture notes. So let us kind of, okay, so AK is equal, still use the notation in the lecture notes. So a QK star A QK, and this QK is just this product. So it should be K minus 2, K minus 1. So it QK, it's this product. It's Q0, Q1, Q K minus 1. Right. And so this is a, well, it's a product of the orthogonal matrices. So it's orthogonal matrix. Right? So first one. So now, and okay. So now, and also kind of, if we kind of define this thing, we can also define our similar thing RK. So, and this will be defined as, I guess it should be defined like this one. So RR K minus 1. So RK minus 2. So R0. So we can define it like that, right? So just kind of, if you define this Q to this RK. So in this here, so the claim number 2. So this claim number 1 explains that when we go along the algorithm, we'll never kind of, the eigenvalues are always the same. Claim number 2 is interesting because it's relevant to why it converges. So, and the claim number 2 is says that claim 2, it says that A to the power of K So if you look at a to the power of k, so it's not with a sub k, which is, but it's just kind of power of matrix A. It turns out, the claim says that it turns out that QR factorization for this matrix is given by this QK and RK. So this is a kind of, well, not obvious, highly not obvious thing. So now we check it. Maybe kind of I might mix the notation here. Yeah, might mix notation. So let's check it, right? So it's proved by induction, of course, and so there should be that A, right, which is a to the power of 1. Okay? So it's so we proof. So the first function is k is equal to 1. So k equal to 1. So in this case, the claim is that A is equal to, Q1, R1. And Q1, by definition, it will be Q0. So it's Q0. And so if it's 1, then this is 0 here. So it's simply Q0. Q0 multiplied by R0. Right? But so this is what we know, that Q0 is Q and R, so it's equal to QR. So this is true because Q0 and R0 were defined as the Q and R, and this is kind of A is equal to QR. So the basis of induction is here, and so the step of induction. So so this might be still useful. So let us remove this thing. So assume that so A k minus 1 is equal to Q k minus 1 R k minus 1. And after that, just multiply this thing on the left by A. So AK is equal to A. Since we don't really know about QK minus 1 much, let us write it in this form. Okay, so what it will be here? It will be Q0, Q1, and ends with, well, according to this notation, K minus 2. K minus 2. And after that, so R. So it starts with RK minus 2 and ends with R0. Okay, so now, right, so let us look at this thing. So here's AQ0. So what we know about A is equal to QR. So it's equal to Q 0 R 0, right? Okay, so it's QR, it's Q0 R0. So now if you look at this thing here, okay, so we see that this is R0 Q0, which is A1. Okay, so this is here, R0 Q0. Okay, so we can write that this is actually equal to Q0 multiply, so multiply by R0 Q0, which is A1. So it's A1 Q1, so on, qk minus 2, rk minus 2, r0. And so it's so on essentially after that. So a1, we know that it's equal to q1 r1. Right, so it's equal to q1 r1. And we'll look at here's r1 q1. Right, so r1 q1 is equal to a2. So the next step will be q0 q1. Here we'll have a r2, sorry, a2. So r1 q1, so a2, and after that q2, and so on. And so qk minus 2, rk minus 2, and so on until r0. So it's clear. So we can kind of continue this until we get something here. So we'll get here a k minus 1. And so we'll get here q0, q1, qk minus, so yeah. So yeah, q so after we multiply, okay, so will be rq minus 2 times q minus 2. So here will be a k minus 1, right? So a k minus 1, and what we'll have here, qk minus 2. Yeah, I think it's right, kind of. So qk minus 2 here, right? And so rk minus 2, and so r0. Right. Okay. So now, so this is not quite. What we want. So now what's that? So why I cannot do anything after that? Yeah, and actually this thing, akk minus 1, it's so maybe we shouldn't kind of at this moment did this kind of transformation. So this ak minus 1 is actually it's actually equal to qk minus 1, right? So the last one here, rk minus 1. And so this is this line here. So we can additionally do additional kind of, well, so transformation and write it. This is qk minus 1, rk minus 1. So it's kind of just nothing kind of, it just kind of we introduce new qk minus 1 and another rk minus 1. Kind of essentially kind of, I think. But after that, we'll look at this thing and look at this thing and see that this is a definition of our qk and rk. So, right, so kind of where qk was defined as q0, q1, qk minus 1, and this is exactly what is written here, q0, qk minus 1, qk minus 2, qk minus 1. So this is by definition equal to this guy. So it's equal to qk r k. And so this is the proof of this statement. So right, so okay, so what kind of, so the question is, so why kind of this is helpful? Well, it's helpful because the powers of AK, and so these are very kind of so this is a kind of related to the finding of eigenvalues. So you know that we had this power method, right? So of finding the largest eigenvalue. So the power method would just kind of start with any arbitrary kind of vector and start to applying this matrix A. Right? So you apply it once, normalize. Apply it second time, normalize. Apply it another time, normalize. And the claim that we said that it will converge eventually to the eigenvector that has the largest, that have a eigenvalue with the largest absolute value. Right? And so this is kind of was the idea. So AK kind of powers of matrix A, they are related to the finding eigenvalues. So now kind of at this moment I'll stop being rigorous, right? So and start to talking about kind of I start waving my hands essentially and explaining kind of why kind of this gives this convergence of AK small. And so and the idea is this one. And so what I need and what I do not need here. Maybe I'll need this thing, and maybe I'll need this thing. I really don't need this one. I really don't need this one. So if you have a, so the matrix A is asymmetric, and we assume that it has a, well, not assume, so it's diagonalizable and have this form. You can write it like that, right? Where U is the matrix of eigenvalues, eigenvectors, sorry, vectors, and is the orthogonal matrix of eigenvectors. So now also let us assume that this lambda, so this matrix lambda, it's diagonal matrix of eigenvalues, right? And well, kind of for simplicity, let us look at the situation when lambda 1 is greater than lambda 2, is greater than so on, greater than lambda n, and assume that actually even they're positive. And so just kind of, well, kind of to be kind of at least understand something a little bit simple. So they're distinct, positive, and there is one largest of them. Okay, so what we can write, okay, so we can write a to the power of k is equal to u. Here's lambda to the power of k u star. Right? So, and if you kind of look at this, it will be something like that. It will be U1, that's a column U2, so on. So UN multiplied by, here's lambda 1 to the power, well, maybe kind of k, right? So to the power of k. And so here will be lambda n to the power of k, and this is the matrix U star. And so now, okay, so if you multiply it, so you do this multiplication, and so so what we'll get? So doing the multiplication is taking this matrix and multiplying the first column. And so it gives you this vector multiplied by lambda 1k. So it will be equal to something like lambda 1 to the power of k multiplied by u1. So this is kind of the first column, right? And after that will be, okay, so now this matrix multiplied by the second column here. Right? So this will give you matrix multiplied by the second column. Only one element here is lambda 2. So it will select kind of the second column here and multiply by this coefficient. So it will be something like lambda 2 k u2 and so on. Right? So the last one will lambda n u n lambda n to the power of k un. And so, and after that multiply by this matrix u star. So okay, so right now, so now what we actually want to see, what's the this matrix AK, what's the columns of this matrix, right? So now so if you look kind of how to find out the columns of the matrix, right? So if you want a matrix, a column of a matrix, you just kind of some kind of S column of this matrix, so AK, and so column S. And so what you'll need to do to take this matrix and multiply by the e to the es, to the basis element S. So, right, so this is just 0, 0, some 1 here, 0, 0. So, and this just takes and separates the column number S. Right? So this is S place, column number S from here. And so if you want to figure out in this situation what you will get, you would get the S column. Right? So if you look, if you want to figure out what's the S column of this matrix, right, then you will get this thing, this big thing, which I will not repeat right now. And after that, U star multiplied by this E S. And so what's U star multiplied by this ES? So this is a S column of U star. Right? So kind of it's U star. So S column of this U star, which is a it's, well, okay, so column of this star, U star S. So it's not U1, U2, UN. It's something different because it's transposed matrix, right? So, but it's S column of this matrix, right? So, and here's this vector. So lambda 1, k u1. So here's lambda 2, k u2, and so on. So the last one is lambda n to the power of k un. Okay, so what's my point actually? Why I'm going to this? All right, so even after that, you can also simplify this a little bit. And okay, so this is this vectors, column vectors, taking the coefficients, which is in this vector. Okay, so okay, so I can continue and write maybe here that this A, K, S column is equal, right? So what it will be? Okay, some coefficient B1, right? So which is in this matrix U star S. Yeah, so this coefficient doesn't depend on K. Right? So it's kind of, it's just some coefficient I'll need to denote in somehow. and it's kind of it depends on S, so maybe kind of I should put here S B1S. But it's not really important. What is this? Could write it in terms of this one. It's clearly something like U S1 or something like that. I'm just kind of not sure kind of which one, but just some coefficient. And here, and after that we will be, so this is a coefficient, after that will be lambda 1 to the power of k u1 plus, and next one will be kind of another coefficient, so b2 of s, right, lambda 2 to the power of k of u2. So, and this is vectors. So u1 and u2, these are vectors. This is a number. These are numbers. So it's a linear combination of these vectors, of the eigenvectors. Okay, so plus so on, plus b n s lambda n to the power of k u n vector. So okay, so that's it. This is what this is the formula that I wanted. So now these coefficients, they don't depend on k. So, and well again, so I'm waving my hand. So assume that they are not zero. Right? So if it's zero, this is not good. Assume that they are not zero. Okay, so this coefficient. So now when k is very large, right? When k is very large, so remember that we assumed that lambda 1 is greater than lambda 2, is greater than so on, greater than lambda n, greater than 0. And so if k is large, then everything, so this term will be much larger than every other term. And so if k is large, if k is large, then every column of AK are almost proportional to U1, to this vector U1. And so, and because kind of these are columns of this matrix. I used this notation. So AKS, right? So I'm looking at this. Every column kind of dominated by this term, So what is this term? It's vector U1 multiplied by some coefficient. So this coefficient is the same for all columns. This coefficient might be different. Right? So for the column. So actually, I need only assume that this thing. So now what I really want is that the first column would be proportional to, the first column would be almost proportional to this U1. So kind of, at this moment, I just need the first column. If the first column is almost proportional to the one, so remember, so what's kind of this thing says? This is a kind of, this is a decomposition, QR decomposition of the AK. But before kind of when we started to talk about the QR decomposition, the QR decomposition actually has a meaning. And so if you have a matrix, if you have some matrix, say in this case AK, right? So and you have a well, so if you have a matrix A, say, right? So if you have a matrix A, and it's kind of, it gives you the column space, and you can kind of write down this column space as a flag, right? So you can write it as a, first of all, A1, so the first column. Right? So span of the first column. After that, you write it the span of the first and the second column. Right? And so let me use this notation as a span. Okay, so then the span of the first, second, and the third column, and so on. And so So the QK, what the QK had, the QK was actually the matrix such that columns gave the orthogonal basis in all of these spaces. Okay? So the first column was the kind of a unit vector in the space spanned by the first column vector of A. So we had this property. So if we denote this V1, this was V2, this was V3, right? We had a property that V1 was span of Q1, V2 was span of Q1 and Q2, right? And so on, kind of. V3 was span of Q1, Q2, Q3. Okay. So this was kind of, so we started with the columns of some matrix, right? Not this matrix right now, kind of just matrix A. Right? And after that, we kind of started orthogonalize them. So we started kind of A1, take the unit vector. After that, look at, take the unit vector proportional to A1. After that, look at V2. So it's, by definition, it's a span of A1 and A2. Right? So kind of find the orthogonal basis in this V2 such that would agree with the previous choice. Right? So the choice of the, so that one of these vectors should be Q1. Right? So, right? And so we build this kind of consecutively. Right? So kind of, if we build the Q1 and Q2, right? So the next one, well, instead of A3, add vector which was perpendicular to Q1 and Q2, right? And still lies in V3. Right? So this Q had a meaning. Right? So this Q matrix Q. So now returning back to this formula. So now we said that QK is actually QK and RK gives you QR decomposition of the matrix A to the power of K. So in particular, that means that the first column vector of the matrix QK must be proportional to the first column vector of AK. So let me write it. Okay, so this is, I maybe don't need. So QK, so first column of QK is proportional to the first column of AK. Okay? So kind of this is kind of the definition kind of QR decomposition. So we're starting the first Q vector, first column vector there is just kind of chosen to be kind of not equal but proportional to the first column of the matrix which we decompose, which we factorize, multiply by coefficient such that make this first column equal have a unit length. Right? But after that, we're going back here and say, okay, so if K is large, then every column of AK almost proportional to U1. So that means that, so almost proportional to U1, to vector U1, to the first eigenvector of the matrix A. Okay, so this U1, remember, this is the first eigenvector of the matrix A. Okay, so first column of this matrix QK, well, it will be clear why kind of we bother about this matrix later. So, but the first column of this matrix QK is proportional to the first eigenvector. What about the second column? So now how we build the second column? Right? So It's like here. So you look at kind of, so second column, it would be kind of, you look at the span of the first two column vectors of a matrix AK in this key. Right? And after that, in this span, you choose a vector which is proportional, which is perpendicular to the vector which you already choose, right, to the first column, right, and have a unit length, right? So what's the span of the first two columns of the matrix AK? Right? So we know, okay, if K is large, then every column of the K almost proportional to U1. This is not good. And it means kind of, well, that kind of V2, the second one, is equal to V1. This is what I don't want this. I want to look at kind of, well, what's the second approximation? Second approximation, right? So second approximation, it means that you need to look at these two things. So the second, so V2 kind of, V2 equal to span of this AK1 and AK2. So first column of matrix AK, second column of the matrix AK. So span of them, it's almost so approximately equal to the span of U1 and U2. So every kind of column vector is have this representation. If you look kind of, well, okay, so almost everything is kind of dominated by this vector. But I need the second approximation. So it makes sure kind of, well, everything looks like this line. Right? But I'll need to see what's the difference from this line. Well, it will be some small difference. Right? So some small difference, and it will be dominated by the second term. So the second kind of span, right? Span of the first and the second column, it will be kind of approximately equal to the span of U1 and U2. And at this moment, I kind of waving my hands a lot, kind of. So it means one space is approximately equal to another space. Right? So I don't really know how to say it exactly, but kind of this is something like that. Right? So you can ignore everything else. Kind of this is the first important terms. So now, okay, so V2 is approximately equal to span of U1 and U2. Okay, so now what about kind of what it means? It means that the second column of QK, okay, well, it's kind of, you already choose the first column is almost proportional to U1. And so you need to choose a perpendicular vector to this. And there is only one perpendicular vector, U2. So it means that the second column of Q to the power of K is approximately U2. Again, so kind of you have a what you are doing, you are kind of applying the QR algorithm to the flag, right? So V1 and V2. So here's V2. You already choose V1 and you knew that it's approximately equal to U1. And so Q1 is approximately equal to U1. So you go in the second step. Second step, or kind of looking at this span and choosing the vector which is perpendicular to your previous choice to U1, right? And scaling it, right? So that it has unit vector. But there is only one vector in this span. It's slightly different from this one, but it's close. Right? So there is only one choice of the vector here, right, which is U2. Right? And this is already normalized. So it must be that the second column of QK is U2, maybe minus U2. Right? So kind of with appropriately choosing normalization at U2. Right? Approximately. Again, so the difficulty is that kind of to make sure that these all approximately have some meaning, but we are not going to do it. But okay, so and after that you see that this is a pattern. Right? So what if after that you look at the third column, say, okay, it will dominate it by the three first terms in this expansion, because lambda 1, lambda 2, lambda 3 in this case will be the largest and will dominate everything kind of after that. And so kind of you'll see that the third column of QK is approximately U3. And so on. You continue, continue. So hoping that this is not breaks argument, even if you do it rigorously. And eventually what you'll get that Q K QK, right? So this QK is approximately equal to matrix U. So matrix U is the matrix with the columns U1, U2. Okay? So it's QK is approximately equal to U. And this is well kind of why kind of. So you actually, if you know QK, you actually know the eigenvectors. And in particular, you can write after that, you can look at this formula and say, okay, so what is written here? So it's QK star multiplied by A multiplied by QK. Okay, so you can write it. So now you know that it's approximately U. Okay, so even kind of before, so A is, I removed it, so it's equal to QK star multiplied by, this one is U lambda U star QK. Okay, so now QK star, it's approximately U star, approximately. Okay, so all we think will be approximately U star U lambda U star U. So this will cancel out and you'll get that this is equal to lambda. Okay, so when this is kind of, so this is what we wanted to prove. AK is approximately, so at this moment, this was approximate, right? So this is identity, this is approximate. This is a step where you do approximation. So it's approximately equal to lambda. So AK should be close to lambda when K is large. Then this argument works. When if K is large, then every column of AK almost, yes. So when this argument works. So this is the idea kind of why kind of the algorithm converges. So I have the intuition that the first somebody discovered the algorithm and after that proved that it works. So somebody playing with the matrices and saying, let's look what happens if you exchange R and Q and multiply them. Right? But kind of this is what it is. Okay. All right, so what can be else said about this? Yeah, so that's it. And there is only 5 minutes, so maybe I will not start the next topic. So the next topic will be, it's kind of related to this proof. So if you want to do this proof rigorously, so none of the book that I saw that kind of everyone kind of says, well, no, kind of. So look at the original paper, how it is done. But one of the ingredients would be look at something which is called Rayleigh quotient. And I think that that's kind of we have a last lecture on Friday. So probably we will look at this lecture on something which is called Rayleigh quotient. So Rayleigh, well, he has a very difficult name. So let me see how it's the right spelling. Rayleigh quotient. And kind of characterization of the eigenvalues in terms of the Rayleigh quotient. And there is actually a very big bunch of theorems related to this, which I will probably not prove, but explain. So this is a kind of a lot of theorem, and this is kind of a big part of the theory of the matrices, I would say. linear algebra, theory of the matrices. So example would be, so you have two matrices, eigenvalue, you know eigenvalues of one of them, you know eigenvalues of another one. So what happens if you add together these two matrices? Can you say something about the eigenvalues of the sum? Right? And it turns out that with Rayleigh quotient, the different characterization of eigenvalues, so different definition of eigenvalues. So it helps you to answer this question. Right? So